we're confident that long term we can design and manufacture a compelling $25,000 electric vehicle.
And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
Yeah, so these, yeah, it's pretty great. And just to clarify, that when we see these plus 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We're starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So this is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time, and where the sort of the electrochemistry is set and the quality of the cell is verified. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
You want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. So, yeah, you can sort of think about like the sort of the fundamental physics of a factory or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation, you've got your exhaust velocity and then the log of the start end masses. So it's basically saying, how fast are things going and what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. So
only the value-added steps.
Yeah, if you break the factory down into cubic meter sections, and say, or smaller, it could be like 1 liter sections, and say is a majority of this volume doing useful work, you would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. So I think it is possible to get to at least 10 times that of volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory. It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to 2 factories basically. And the company that will be successful is the company that with 1 factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we with 1 factory achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Highbar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps.
Yeah, I mean, basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible. But I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. And what we do is essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet, and this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat, and you have carbon fiber face sheets and say aluminum honeycomb between them, this gives you incredible stiffness, and it's really the way that any super fast thing works. Is you create basically a honeycomb sandwich with 2 face sheets. This is actually even better than what aircraft do, because aircraft do not do this. They can't do this because fuel is liquid. So in our case, the batteries are solid. So we can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car.
Yeah.
In fact, if this was a convertible that had no upper structure, it would be stiffer than that convertible would be stiffer than a regular car. So it's just really really major. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to use to move the cells closer to the center of the car. Because we don't have the in the top one, we've got sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack. And we can actually bring the cells closer to the center. Because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also proves what's called the polar moment of inertia, which is that you can think of like when there's a ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't want to know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah. Yeah.
All right, so stacking it up, we're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. And yeah, so I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah, just happened to happen out that way.
I mean, 0.420%, of course. Yeah, so what this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So, you know, it's not like if we could do this instantly, we would. But it's really, I think what this bodes, it just really bodes well for the future, and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. So, you know, what tends to happen as companies get bigger is things tend to slow down. Well, actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
Yeah. I mean, long term, we want to try to replace about, you know, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
What does this mean?
What does it mean for what does this mean for our future products? So, you know, we're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. So, you know, this has always been our dream from the beginning of the company. I even wrote a blog piece about it because you know, our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a, I don't know, mass market premium, but you know, like the Model 3 and Model Y. But really, it was always our goal to try to make an affordable electric car. And I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah.